On this lovely day, we are going to describe and identify patterns. We are going to be the Sherlock Holmesian of whoop, whoop, whoop. Nice. Man, they call me les artistes. They call me Swenson les artistes. They do. No, no, no. So on this puppy here, OTT, FFSS, 6, 7, 8, 9, 10, 11. All right, so let's walk through some things. The key thing, absolutely key thing about all success in algebra, in geometry, whatever math class, is patterns. Looking for patterns, trying to describe those patterns. So let's take a gander here and see if we can compile the data into some sort of thing that explains the data, okay? So let's take, for example, this one here. I see that this first shape has 2 squares, and my second shape has 4 squares, but how do I get from here to here? Well, effectively, all I did was add the same type of row underneath it. Well, how do I get from the second figure to the third? All I did was add another row. Looks like to the bottom, but theoretically could be on the top as well. So I keep adding a row from one to the figure. So how would we describe that right there? Add a row of 2 squares to the bottom. Add a row of 2 squares to the bottom. So it asks us to draw the next one. And I tend to draw bigger than they give me because I prefer the space. And there we go. That would be my 5th figure. 3rd figure, 4th figure, 5th figure. So we recognize that there is a pattern. We're just adding something to the bottom. We described it using words, and let's see mathematically if there is a way to describe it by a table. The first figure, I have 2 squares. The second figure, I have 4 squares. Clearly, we see the pattern continues on, 6, 8, and 10. You may or may not have heard of this before, called a process column. A process column is just, how do I get from this column over here to this column over here? What's the process that goes on? Now, sometimes it's very straightforward, and sometimes we just don't know, and we might need to leave the process column blank. So, in this first example, to get from a 1 to a 2, well, I could add 1, but does that work always? Does that work down here? 2 plus 1 is not 4. And so, got to undo that. It's not plus 1.
Times 2.
So let's try times 2 and see if that works. So I take my column 1, or my problem from there. Do I double it? And does that give me 2? So far, so good. Let me take my 2. Let me double it. Oh, good. The process column is, what's the thing I keep doing over and over and over again? And it seems, in the end, I am just going to double. Whatever figure I'm talking about, double it to tell you how many squares I have. So maybe to describe this, we say add 1 more row with 1 more block or square. So I will do a speedy version of it with dots to get like that. That's just speedy up. Okay, now it's very easy to talk about figure 1 and figure 2 and figure 3 and the number of squares. The first figure just has 1 square. The next one has 3. The next one has 6, 10, and 15. This one's a little bit harder to talk about, But how do we get from here to there? How do we get from a 2 to a 3? How do I get from a 3 to a 6? All right, a few things we want to define before we jump into further content. And first off, a variable. A variable changes, hence the name variable, varies. Examples of variables would just simply be x, n. Letters are generally what we use for variables. A constant, on the other hand, is something that never changes. Yesterday, x could be 2, but today, x might be 13, depending on the problem. However, a constant like 6 or pi or 3.14 or 1/2, these types of numbers will never change. Tomorrow, 1/2 is still 1/2. So that is called a constant. It doesn't change. Immutable. Numerical expression. Things like 6 plus 3. Things like 15 times 11. These are just operations and numbers. Numbers and operations. So by extension, a variable expression will just be numbers, letters, and operations together. 6x plus 3. There you go. Now we have a variable expression. All right, so let's take a gander here at this process table. What we're going to look at is we've got some input data, we've got some output. We're going to try to figure out how to get there. And in the end, we're going to end up discovering what we might call the function. What is the one rule to rule them all? How do I get from one column to the other using any number or any letter? So let's see here. We might need to experiment at first. So 1 to 4. How do I get from a 1 to a 4? Well, maybe I add 3. Does that always work? Add 3 here. Oh, hashtag no, it doesn't work. All right, so adding 3 doesn't work. Now, it is true that if you multiply the 1 by 5, and then you subtract 1, you get your 4. Really? But how did we come up with that? Did we just pull that out of the air? Let's see some magic here. Notice to get from the 4 to the 9, I add 5. To get from the 9 to the 14, I add 5. Oh, look, what are we doing every single time? We're adding 5. So this right here is called the constant of variation. That's sort of weird that you have a constant of change. Something that changes, but it changes the same every time. So you're always increasing by 5. When we talk about like how much if you buy a song online for 99 cents, that one's 99 cents. But what if I bought 10 of them? How much is it? Oh, it's 10 times 99. That's it. It is the 99 cents doesn't change, but the fact that I bought 10 of them does change. So that's where we got the 5 from. How do we get the -1? That's kind of just an adjuster. Sounds a little bit complicated. Sometimes for this column, you're just exploring. And sometimes if you don't see it, it's okay if you don't see it at first. Try a few things. I don't get it, put a question mark by it. It's understandable. Okay, so how about this one? Notice I'm just adding 5 right here, so I already know what the next number is, even if I don't know how I got it from a 5. But how I got it from the 5 was I took the 5, I quintupled it. You like that word? Quintuple. And then I -1. So this one here would be 5n minus 1. You take your number, quintuple it, multiply by 5, and then subtract 1. The benefit of what we just did, now if we have to go to 2,000, we don't have to make the table. We just put 2,000 in, and we get it. Where the -10 came from, here we're just subtracting 2 every time. Subtract 2, and there we go. Now the real question is, how do I get from there to there? What operation are we doing? Go ahead. Good. So if we take each one of these, take for example the 4, and we double it, of course with an opposite, we now have our expression. So negative 2n is what we get there. Negative 2n. A gardener plants a flower garden between his house and a brick pathway parallel to the house. The table at the right shows the area of the garden in square feet, depending on the width of the garden in feet. Now, one way to solve these two problems is just to keep the pattern up, right? I could do a 5 right there and put a number there, get a 6 there, a 7 there, and an 8 there. The problem is, even to get to 15, I have to keep adding and adding and adding and adding. So instead of trying to complete the the table this way, I might want to figure out, well, what's the one rule that tells me how do I get from this column to that column? So what do we discover? Well, how does it change from each one? What does this go up by from the 3.5 to the 7? We add 3.5 there. So let's see, does that follow? From the 7 to the 10.5? Oh, look, I add 3.5. So what we notice is it changes, but it constantly changes. It changes with something that doesn't change. So how might we describe this? Would be something like this. The area is going to be 3.5 times my width. The area is 3.5 times my width. Now that feels like a big jump maybe to get from one place to the other, but that's essentially my process column. How do I get from here to here? Multiply by 3.5. Multiply by 3.5. Multiply by 3.5. So now all we have to do is plug and play rather than actually keep adding, keep adding, keep adding. So for part A, my area is going to be 3.5 times 8. That's ocho for you polyglots. And that's going to give me 28 square feet. Finishing this one up on part B, the area of the garden at 3.5 times 15 feet wide, and we get 52.5, confirm? Okay, square feet. Again,